In this video, we're going to learn the third learning objective, which is all about the dividing out technique. So let's see what this technique is telling us. So, right, to explain the dividing out technique better, I want to go with an example. So we have a rational function, x squared plus x minus 6 divided by x plus 3. The limit point is -3. So normally, if you have a rational function, the first thing that we can use is the direct substitution. So minus 3 squared plus minus 3 minus 6 minus 3 plus 3. If you simplify this, you get 0 over 0, so the direct substitution does not work at all. So in other words, the result that we had earlier, that's theorem 2.3, direct substitution to evaluate the limit of rational functions, fails to apply for our problem. Now here the problem is that not only the denominator becomes 0, but the numerator at the same time becomes 0. That's why you had a 0 over 0 type undetermined, indeterminate form. So what we can do here is that we can factor out the top, which is a quadratic. We know how to factor that out. If you don't, please refer back to the algebra formula card. So this quadratic can be factored into x plus 3 and x minus 2. So if you don't remember, by the way, I can quickly tell you a shortcut to find the right factorization here. So what you do here is to factor x squared as x times x, and then you're going to factor this number in a way that the product of the numbers would be -6, but the sum would be this coefficient here. So in other words, you're looking for two numbers whose product is -6 and the sum +1. Those numbers are +3 and -2. And as you see that x plus 3, x minus 2 would be the factors of the quadratic. Now luckily you have x plus 3 at the top, you have x plus 3 in the bottom, so you can actually divide them out. Remember, the name of the technique is called dividing out technique. So there you go. If you divide them out, you have a brand new function here, x minus 2, and that's going to be exactly what the g is in the theorem that we just mentioned. And f and g match everywhere except at -3, as you see. So therefore, the limit of f of x is exactly equal to the limit of g of x, because f and g match everywhere except -3. But this limit can be easily calculated as -3, -2, which is -5, by direct substitution. And here are a few important remarks coming out of this example. So here, the direct substitution spot out 0 over 0 type indeterminate form, okay? And because you cannot determine the limit here, I mean, it's 0 over 0, we don't know what that is. And if you evaluate a limit and encounter this kind of form, the obvious way to handle this problem is the dividing out technique, if you can, so that when you rewrite the fraction or the rational function, so hopefully the new denominator doesn't have 0 as you pass the limit, okay? So again, one way to do that is just what we have seen. It's called the dividing out technique, and common factors are divided out, and you have a brand new function g for which you now have to find a limit for. All right, in this video, we worked on the dividing out technique, which is algebra heavy. It could be algebra heavy, so make sure like you check out the algebra formula card to be able to carry out factorizations if needed. All right, so I'm going to finish this video right here, but watch my next video, which is going to be called the rationalizing technique. That's another learning objective, and I'll see you in that video. Bye.